Hi, I'm Violetta, and I'm excited to share our current research on speed measurements of classically forbidden motion. But before diving into the details, let's start with the basics. Occasionally, quantum particles are caught passing through the barriers they don't have sufficient energy to surmount. We call this quantum tunneling. Every physicist is familiar with this phenomenon from the basics course of quantum mechanics. However, some aspect of this phenomenon remains unresolved for decades. For example, physicists have never agreed on the answer to the question how much time does a particle spend inside the potential barrier during tunneling? Or equivalently, what speed does a particle acquire? Here is where it gets interesting. Certain theoretical and experimental studies suggest that the tunneling time decreases and consequently speed of particle increases as the energy of the incident particle diminishes. This counterintuitive idea challenges established principles and sparks discussion about violation of causality and faster-than-light motion. And this speed increase is what we test in our work. To measure the speed of classically forbidden motion, we first delve into how velocity is treated in quantum mechanics. Quantum mechanics offer various velocity definitions, such as phase velocity, group velocity, velocity derived from the probability density current, or equivalently from the momentum operator. As an example, let me explore two cases. The first case is a velocity derived from the probability density flow, and this expression is also known as Gaussian equation in Bohmian mechanics. And the second case is a velocity derived from the momentum operator. The main difference is that the first equation describes velocity only to phase gradients of wave functions, ignoring density or amplitude gradients. And if we consider the case of classically forbidden motion characterized by an evanescent wave, it will give us zero velocity since the absence of the phase gradients. However, the presence of particles indicate motion and consequently non-zero speed. At the same time, the velocity derived from the momentum operator considers amplitude gradients, which leads to non-zero velocity. These two examples reveal some tension in the determination of velocity. In our work, we introduced a novel scheme using coupled waveguide potentials, where the population transfer acts as a clock, enabling us to measure the speed of the particles along the waveguide axis. Applying this scheme to evanescent phenomena at the reflection potential step, we reveal an energy-speed relationship for classically forbidden motion. Surprisingly, our findings show that the smaller the energy of the incident particles, the higher the measured speed inside the potential barrier. Our research sheds light on the complementary roles of phase and density gradients in quantum mechanical wave function, challenging the Bohmian interpretation. Our findings can be seen as a critical test of Bohmian trajectories in quantum mechanics. Furthermore, our research endows to the ongoing tunneling time debate and helps to disentangle various physical phenomena that contribute to this problem. In conclusion, our study offers a fresh perspective on the speed measurements of classically forbidden motion. By addressing long-standing questions, we contribute valuable insights to the broader scientific community and stimulate further exploration of this fascinating field.